Welcome viewers, in this video we'll see the single phase AC series motor. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic single phase AC series motor. The DC series motor is converted into AC series motor. Further, what are the procedure, what are the modification we need to do, that we'll see in this video. In a DC motor, if direction of field and armature current is reversed, the direction of torque remain unchanged. So the DC motor rotating in forward direction, if you want to reverse, either field or armature is reversed means it will rotate in reverse direction. But the torque remain unchanged. There is no change in the torque. Only the direction will reverse. Therefore, when DC series motor is connected to AC supply, both field and armature get reversed and unidirectional torque gets produced, and so the motor can work on AC supply. So based on that, if we apply the AC supply, the unidirectional torque will be produced, and so that this motor can work on AC supply also. So we can easily convert DC series motor into AC series motor because unidirectional torque is produced. But we have some disadvantages, some modifications are there, that we will see that one by one. But it has certain disadvantages. What is that? First one, high eddy current losses in yoke and core, which causes overheating. Because of AC supply we got high eddy current loss. Armature and field winding offer high reactance to AC, due to which the operating power factor is very low, right? So the reactance will be more in the armature and field winding. So we are using AC supply, so automatically due to high reactance the power factor is very low. Then third one is because of high voltage and current in the short circuited armature coil, during commutation sparking takes place at the brushes. In case of DC, we have sparking is there, but while connecting the AC, the voltage and current is very high. So the sparking also takes place in the commutation at the brushes. Now we'll see what are the modifications to do overcome these disadvantages. Some modifications are made on DC series motor when it is connected to AC supply, when it is called a AC series motor. So we need to do some modification. Then it is called a DC series motor can be called as AC series motor. Now we'll see what are the modification we need to do. To reduce eddy current loss, the yoke and core is laminated. So by laminating the yoke and core, we can reduce the eddy current loss. And the power factor is improved by reducing field and armature reactance. Field reactance is decreased by reducing number of turns, but this decreases the field flux, thereby increasing the speed and decreasing the torque. So power factor is improved by reducing the reactance. While reducing, what happened? Reducing means reducing the number of turns. While reducing the number of turns, the flux will decrease. If flux decreases, the speed, thereby the speed will increase, thereby torque will decrease. So we need to compensate. We need to reduce the number of turns accordingly, otherwise the torque will decrease. And other things are, so to keep torque constant, it is necessary to increase the armature turns, which increase the armature inductance, which causes the severe armature reactance, right? The torque is reduces. So to keep the torque, we need to increase the armature turns. While increasing armature turn, what happen? Armature reactance will increase, will cause the armature reactance. Then how to reduce that? Therefore, to neutralize the armature reaction, it is necessary to use the compensating winding. So this thing can be eliminated by using the compensating winding. In compensating winding, there are two methods available: cumulatively compounded and differential compounded. First we will see the cumulatively compounded, diagram A. So this is the armature rotating part, this is a field winding, main field winding. So in series with main field winding and armature, the compensating winding is connected. So both are added together, so it is called conductively compensated. right? The compensating winding is connected in series with field and armature. Now we'll see the second method. So this is called inductively compensated, diagram B. So in that what we did, the compensating winding is available separately. It is short circuited. It acts as a secondary transformer, secondary of the transformer. It is connected in as a secondary of the transformer. In earlier case it is connected here. So conductively compensated. Now it is inductively compensated like a transformer. Now we'll see in both the cases what will happen. If the compensating winding is connected in series with the armature as shown in the diagram A, the motor is said to be conductively compensated. If the motor is to be operated both on AC and DC, then the compensation must be conductive, right? So it is conductively compensated because current is flowing in series. Both are connected in series. If the compensating winding is short circuited on itself, as shown in the diagram B, the motor is said to be inductively compensated. There is a inductance happen. Hence the compensating winding acts as a secondary of transformer and armature is the primary. So inductively it is compensated, armature acts as a primary winding, compensating winding acts as a secondary winding. Now we'll see the further detail. To reduce the induced EMF due to transformer action, the armature coil during the commutation period, the following measures are taken. So during commutation period, the sparking happened because of to reduce the induced EMF. First, flux per pole is reduced and number of poles are increased. So the flux per pole is reduced. The number of poles are increased. Frequency of the supply is reduced. Single turn coils are preferred, right? So these are all the measures to reduce the commutation. The starting torque is about 3 to 4 times of full load torque, right? Now we'll see the speed torque characteristics followed by applications. So this is the speed torque characteristics. In x-axis we have torque, y-axis speed is there. When the speed increases, what happens? The torque is, when the torque keep on reduces, it is going in a inverse manner, inversely parabolic, reduces in a parabolic manner, right? The torque is initially, the torque keep on increases, the speed is decreasing gradually, the speed at this is more, thereafter decreases, the torque is increasing gradually, so it is inversely proportional. This is AC series motor, this one DC series motor. So the AC series motor having lesser value, DC series motor having more value, right? The speed and torque is inversely proportional. We already know that in series motor it is inversely proportional. It is decreasing in a, the speed is decreasing in a parabolic manner. But the value is more in DC. In case of AC it is lesser. The value is lesser. What are the applications? Due to high starting torque, it is used in electric traction, hoist, locomotive, etc. Very similar to the DC series motor, that also used in the traction and hoist and locomotive. So in this video we discuss how we are converting DC series motor into AC series motor. What are the methods? What are the advantages? What are the compensating techniques we discuss? Speed followed by speed torque characteristics and applications. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. All the best for your examination. Welcome viewers. In this video we'll see the construction and operation of a hysteresis motor. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, hysteresis motor. We know that hysteresis effect is nothing but during magnetization and demagnetization, the power will be lost in the form of heat. That is, the power will decrease during magnetization. If the power increase means during demagnetization the power will decrease. I know that we have the hysteresis loop, we already is available. So there is a energy loss in the form of in the form of heat is called a hysteresis. Based on that, this hysteresis motor is working based on that hysteresis principle. The operation of this motor depends on the presence of a continuous revolving magnetic flux. So it is based on continuous revolving magnetic flux. What is continuous revolving magnetic flux? The field winding, the flux is produced in a winding. If single winding is there, while passing the current, the flux produced by positive half cycle is cancelled by negative half cycle. So there is no net flux. During positive half cycle, positive flux created. During negative half cycle, negative flux is created. So got cancelled. So what we need to do, minimum 2 phases should be there. In case of 3-phase motor, 3 phases available that are displaced by 120 degree. So always there is a revolving magnetic field is available because of 3 phases with 120 degree displacement. In case of single phase winding, if only one winding is there, net flux is 0. So due to that, we are using 2 phases with 90 degree phase difference, so that there is a revolving magnetic field will be created. So based on that, it is working with the revolving magnetic field. So we need a minimum 2 phases with phase displacement. We will see how we are getting that. Hence for the split phase operation. So here we are using split phase operation. It stator has 2 windings which remains connected to the single phase supply continuously, both at starting as well as during the running of the motor, right? So it is a split phase operation. 2 windings are there. It is continuously connected to the AC supply during running as well as starting. We will see how we are getting the phase difference. Another condition is phase difference. So usually shaded pole principle is employed. Shaded pole. So we have one copper coil is there, that is called a shaded pole. So that will produce the phase difference between the windings that we'll see during the diagram. For this purpose, giving shaded pole hysteresis motor. So it is called a shaded pole hysteresis motor. Alternatively, stator winding of the type used capacitor type motor may be used, giving capacitor type shaded pole motor. So in addition, capacitor also available, right? So in either type, no centrifugal switch is used. Normally centrifugal switch is used to disconnect the starting winding after motor attain the rated speed. Due to based on the centrifugal action, the centrifugal switch will disconnect the starting winding. But here during starting as well as running, both the windings are connected. So centrifugal switch is not used. The rotor is smooth chrome steel cylinder having high redundancy, so that hysteresis loss is very high, right? It has no winding. This rotor not having winding, only the steel cylinders are available. Now we'll see the diagram. So this is the hysteresis motor. Rotating part, rotor is available. These are the stators. 4 coils are available, 4 poles. So this is the shaded pole. It is diagonally opposite, we have shaded is available. What will happen when the current is flowing? Some of the EMF, some of the flux will link with the shaded pole. Due to that, current flowing through the shaded coil and EMF is induced in the shaded coil. That EMF is having 90% and 90 degree phase difference with the main flux. The flux produced in the shaded coil and the main flux having 90 degree phase difference, so that we are getting the revolving magnetic field. Our aim is to have 2 windings, then 90 degree phase difference. 2 winding is provided by one main winding, in second is the shaded pole. Main winding is the one winding, shaded pole is the second winding. So because of the magnetic field induction action, the flux produced in the shaded pole having 90 degree phase difference with the main flux. So we are getting the phase difference also. So due to the rotating magnetic field will be created. Shaded pole induction motor, separate video available. In that full explanation is given how we are getting the 90 degree phase difference. So this is the exciting coil. Now we'll see the description. In above diagram, it is a two-pole shaded pole type hysteresis motor used for driving ordinary household electric clocks. So here two-pole shaded and with a shaded pole. The rotor is thin metal cylinder and the shaft drives a gear train. Thin metal cylinder and also gear trains are available. Because of high retentivity of the motor of the rotor material, it is very difficult to change the magnetic polarity once they are induced in the rotor by the revolving flux. High retentivity is there, so very difficult to change the magnetic polarity. We'll see the other detail. The rotor revolves synchronously because the rotor poles magnetically lock up with the revolving stator pole of opposite polarity. So it is almost rotating in a synchronous speed. However, the rotor poles always lag behind the stator pole by an angle of alpha. That is based on the shaded pole. The flux in the shaded pole oppose a 90-degree phase difference with main flux, so that there is a phase difference of 9 alpha angle between the pole stator and rotor poles. We'll see the further detail. Mechanical power developed by the rotor is Pm equal to Ph of 1 minus S by S. This mechanical power developed Pm. Ph is hysteresis loss in rotor and S is the slip. We know that the slip of the motor. Also the Th, the torque is 9.55 Pm by Ns. It is seen that hysteresis torque depends solely on the area of rotor's hysteresis loop, area of the rotor. It is not depends on any other parameter, only based on the area of the rotor. So based on that, we will see the further detail. The fact that rotor has no teeth or no winding of any sort result in making the motor extremely quiet in operation. The noise is not there, sound will not occur, and free from the mechanical and magnetic vibrations. So it will run smoothly. There is no mechanical magnetic vibration and it operates quiet operation. So the noise are not available. This makes the motor particularly useful for driving a tab decks, turntables and other precision audio equipments. So the sound is not there. So wherever we need the audio equipment, tables, tab decks, we can use this motor. Since commercial motor usually have two poles, they are run at 3000 rpm at 50 Hz single phase supply. So approximately they are having two poles, so it is almost running at 3000 rpm. In order to adopt such a motor for driving an electric clock and other indicative devices, gear train is connected to the motor shaft for reducing the load speed. So this motor can be used in an electric clock and indicative devices. In that the speed we need to go with our required speed. So the normal speed is 3000 rpm. So our required speed can be get by the gear system. By using gear system we can obtain we can control the speed. Now we'll see other details. The unit accelerates rapidly, changing from rest to full speed almost instantaneously. So from no speed to full speed can be get instantaneously. It will not take any more time. Instantaneously it will changes from no load to full load, no speed to full speed. It must do so because it cannot accelerate gradually as an ordinary motor. It is either operating at synchronous speed or not at all. So it will not rotate in any other speed. It will rotate in synchronous speed. Otherwise it will not rotate. Then we'll see some unique features of this motor. Some unique feature of the hysteresis motor are, since its hysteresis torque remains practically constant. So we are getting the hysteresis law that is almost constant from locked rotor to synchronous speed. A hysteresis motor is able to synchronize any load. It can be accelerated, something so other motor does. right? So we have hysteresis star that is almost constant. It is rotating at synchronous speed. So we are able to synchronize any load. Can be accelerated. That load it can be accelerated. So it can be accelerate any load at a synchronous speed. That is a unique feature. And the next one is due to its smooth rotor. We already know that there is no noise, there is no vibration. So the motor operates quietly and does not suffer from the magnetic pulsation caused by slot or salient pole that are present in the rotor of the other motors, right? So the two important feature is one is hysteresis star rotating at synchronous speed, so it can able to accelerate any load. Another one is not affecting with the magnetic magnetic pulsation and vibration, and quiet, it is not producing any sound. That is the another feature of the hysteresis motor. So in this video we discuss about the hysteresis motor, how it is differ from other motor construction wise, what is the operation, what are the unique features available in the hysteresis motor. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. All the best for your examination. Welcome viewers. In this video we will see the details about repulsion principle followed by repulsion motor. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. Repulsion principle, repulsion motor. First we will see conceptually what are the details available in the repulsion motor. Stator winding of the distributed non-salient pole type housed in the slots of a smooth cored stator. So is a distributed non-salient pole projection is not there. They are housed in the slots of smooth cored stator, just as in the case of split phase motor. The stator is generally wound for 4, 6 or 8 poles. So this is the detail about the stator. Now we'll see the rotor. The rotor slotted core type carrying a distributed winding, either lap winding or wave winding, which is connected to the commutator. The rotor is identical in construction to the DC armature. So rotor is very similar to the DC armature. Brushes, commutator, lap winding, wave winding is very similar to DC armature. Now we'll see the commutation process. A commutator which may be of one of the two types. First one is an axial commutator with bars parallel to the shaft. Axial commutator. Another one radial or vertical commutator having radial bar on which brushes press horizontally. One is axial commutator parallel to the shaft. Another one radial or vertical commutator having radial bar horizontal, brushes press horizontal. Carbon brushes fitted in carbon holder which ride against the commutator and are used for conducting current through the armature winding, that is rotor winding. So the commutator available mean automatically we have carbon brushes. So that fitted in the carbon brush holder with a ride against the commutator and used for current, conducting current through the armature winding. Now we'll see the repulsion principle. So we'll see the repulsion principle. To understand how torque is developed by repulsion principle, consider the diagram which shows a two-pole salient pole motor with magnetic axis vertical. For easy understanding, stator winding has been shown with concentrated salient pole construction. Right? Now we'll see the diagram. Two-pole salient pole with a magnetic axis vertical. We'll see the diagram now. So this is the two-pole salient. So this is the stator, top one. Then this is the rotor portion, and bottom we have another one more pole of the stator. So it is stamped as y dash. The axis is stamped as y y dash, right? So now we'll see the what happened in the rotor. So rotor, the brush holders, brushes are available. So these are all the EMF and current direction, plus and negative. So this brush holder, brush is available aligned vertical with the magnetic axis. It is available vertically. So this is the stator pole, N pole. This is the rotor, N pole. Both are same. Both stator as main pole as well as rotor pole having N at the top. Similarly, S at the bottom. So there is a repulsion will happen. Both will repel each other. So that is called a repulsion motor. The important thing is the brush holder aligned vertically. In that position only the EMF will be generated and current will be flowing through the rotor circuit because of the vertical position. Now we'll see what will happen in the horizontal position. So this diagram refers the horizontal position. The brush holder is available horizontally. Remaining all are same. At the top, main pole and rotor pole is N. Bottom, main pole and rotor pole is S. The axis is y dash. So in this case, there is no EMF is induced. Only in vertical case, the EMF induced, and the brush holders are available in the horizontal mean the EMF is not induced. So this is therefore the diagram B. Vertical position diagram B, vertical position diagram A, horizontal position diagram B. Now we'll go to the description. Right, so these two poles, alien pole, just now we referred. Now we'll go to the remaining description. The basic function of the machine will be same with the either type of construction. Both are almost same. Only the brush holders are different. Vertical diagram A, horizontal diagram B. As mentioned before, the armature is of standard DC construction with commutator and brushes. The armature is very similar to the DC motor. Suppose that the direction of flow of a alternating current in the exciting or field winding in such a way that it creates N pole at the top, S pole at the bottom. So that we will discuss in the diagram itself. N pole is available at the top, S pole at the bottom because of the exciting, the direction of current and EMF. Based on that, the poles are created. The alternating flux produced by the stator winding will induce the EMF in the armature conductor by transformer action. Right? So this alternating flux is produced by the armature winding will induce the EMF in the armature. So only in vertical position, brushes are vertical position, the EMF is induced. Horizontal position, EMF is not induced. That we refer in the diagram A and diagram B. Now we'll go to the next description. The direction of induced EMF can be found from Lenz's law and it is shown in the diagram. The EMF and current directions are shown in the diagram A. Diagram B, there is no EMF induced and current. That can be calculated by the Lenz's law. However, the direction of induced current in the armature conductor will depend on the position of the short-circuited brushes. So these short-circuited brushes will decide the induced EMF direction. That is in the vertical position, EMF is induced. Horizontal position, EMF is not induced. So this is based on the short-circuited brushes. If the brush axis collinear with the magnetic axis of the main pole, the direction of the induced current will be as shown in the diagram A. First diagram, vertical. The brush positions are aligned vertical. In that EMF is induced, that we refer in the diagram A. As a result, the armature will become an electromagnet with the N pole at the top, directly under the main pole, main N pole, and with S pole at the bottom directly over the main S pole. Right? So at the top, main pole is N and armature pole also N. At the bottom, main pole is S, armature pole also S. Now we'll refer the diagram once again. So this is the N pole, main N pole, rotor N pole. At the top, rotor S pole, main S pole at the bottom. This is the diagram A. The brushes align vertically, so current directions are clearly indicated in this position. Now we'll go to the next position. So the top N pole, bottom S pole. Because of the face-to-face positioning of the main and induced pole, no torque will be developed. So at the top both are N pole, at the bottom both are S pole. So there is a repulsion takes place. So that induced magnetic pole and no torque will be developed. The two forces of repulsion on top and bottom along with YY direction, YY in direct opposition to each other. So that are opposing each other. Right. If brushes are shifted through 90 degree, that is diagram B, the brushes are held in a horizontal to the position shown in diagram, so that the brush axis at the right angle to the magnetic axis of the main pole. The direction of induced EMF voltages at any time in respect to the armature conductor are exactly same as they were for the brush position of diagram B. Right. So in the next, what we are doing, we are shifted to 90 degree. Brush positions are shifted so that the brush and the brush axis is right angle to the magnetic axis at 90 degree. So the direction of induced voltage at any time in respect to the armature conductor is very similar to that is given in the diagram B. Now we'll refer the diagram B. So this is the diagram B. So this is the main axis, magnetic axis, brush axis, both are 90 degree. It is displaced at 90 degree. Refer diagram B. So now we refer the diagram B. However, with brush position of diagram B, the voltages induced in the armature conductor in each path between the brush terminal will neutralize each other. That's why we already discussed. In vertical position, EMF induced with the direction also given in the diagram A. In horizontal position, there is no induced EMF, so that there is no current direction given in diagram B. Right. So in diagram B, horizontal magnetic axis and brush holders are 90 degree to each other, but it will produce both induced EMF and armature current, but it is neutralize each other. Hence there will be no net voltage across brushes to produce the armature current. Right. Diagram A and B very similar. In diagram B also it will induce the EMF, but that is neutralize each other, so there is no possibility of flow of current. I will see the remaining. If there is no armature current, obviously no torque will be developed. If the brushes are set in the position as shown in the diagram A, so that brush axis in neither in the line nor 90 degree from the magnetic axis YY of the main pole, a net voltage will be induced between the brush terminal, which will produce the armature current. Right. So in position A only will the EMF will be induced, the armature current is flowing. B also it will same, but it is neutralized. The armature will again act an electromagnetic, it develop its own N and S pole, which in that case will not directly face the respective main poles. Right. Again it will develop the electromagnetic and develop its own N and S pole. Right. Now we'll see the another one more diagram. Now we discuss vertical position, horizontal position. In between, inclined, if it is inclined with angle alpha. So as shown in diagram C, the armature poles lie along AA, making an angle of alpha with YY. Right. So there is a angle. Horizontal, vertical is there. In between, now it is having with an angle of alpha. That refers the diagram C. Now we'll see the diagram C will refer. So this is refer the diagram C. the top we have N pole, what we discussed earlier. At the bottom S pole. The axis is Y, Y dash, diagram C. Now the rotor is having an angle of alpha, this A dash and Y dash. Between Y dash and A dash there is an angle of alpha. So in this position also there is a EMF will be induced and the motor rotates. So that refers in the diagram D. See this. So this inclined, now it is inclined. Earlier case, the diagram A. Here also main pole N, rotor pole also N. Rotor pole S and main pole is S. So there is a repulsion. Now it is rotated. It is inclined angle of alpha. So now see the position. This diagram D refers. This S pole and N pole. Now it is rotor is with an angle of alpha. So this S and N attract each other. This N and S will attract each other. So it will start rotate. So this direction indicated as in the diagram, it starts rotates. Right. So this diagram C shows the rotor position with an angle alpha. Diagram D will shows how it is attracted and what is the direction of rotation. Now we'll see the description. Hence the rotor N pole will be repelled by main N pole, and rotor S pole will similarly be repelled by the main S pole. Right? Attracted as well as repulsion also takes place. Consequently, the rotor will rotate in clockwise direction as shown in the diagram D. Now we'll refer the diagram D again. So these two are attracted, not only these two are repelled each other. So this main thing is the repulsion motor. There is a repulsion takes place between these two main N pole and rotor N pole. Similarly, main S pole and rotor S pole. So there is a repulsion takes place so that it rotating in the clockwise direction. Mainly we are focusing repulsion, not a attraction. Right? This repulsion motor, so that the basic principle repulsion. So there is a repulsion that takes place between main and rotor pole here also. Yes, both are yes, repulsion takes place. Since the forces are those repulsion, it is appropriate to call the motor as repulsion motor. Because of this, called as a repulsion motor. So principal shortcoming as of such motors are. So what we discussed, the brief discussion is given. Speed varies with changing load, becoming dangerously high at no load. So the speed which varies, changing load is changes means speed will vary. That will be dangerous at the no load. So we have more speed is there. So we need to check the no load is there, then dangerous speed will be there. Low power factor except at high speed. High speed means no problem. If it is low speed means the power factor will be low. Tendency to spark at brushes. It's a common problem. As a DC motor having common problem, sparking. So here also the sparking is occurs. Now we'll see some more details about the repulsion motor, speed, torque characteristics, and other. And what is the current and torque direction. We'll see. Now we'll see the speed, torque characteristics followed by the direction of torque and speed. It should be noted that if the brushes are shifted counterclockwise from Y dash, rotation will be also the counterclockwise. So the rotation of motor based on the rotation of the brushes. Obviously the direction of rotation of the motor is determined by the position of the brushes with respect to the main magnetic axis. Right? So the rotation is based on the brushes with respect to the magnetic axis. Now we'll refer the diagram. So this diagram is given, only the rotor portion is there. This is stator available. Refer the diagram E. So this is the direction of rotation, clockwise. Then the alpha angle, that is the angle between main axis and brush axis, alpha. So this alpha also determine the torque. Torque developed by the motor is determined by the alpha. We discussed the magnetic axis is vertical, the the current and EMF will be generated. If it is horizontal, the EMF will be generated, but it is neutralized. In between, with the inclined angle between main axis and brushes, that is nothing but alpha. In that, the torque is keep on increases. Right? So this diagram will give the direction of rotation of the motor, direction of rotation of the torque, and direction of rotation of the angle alpha. That is, alpha is the angle between main magnetic axis and brushes. So this refers the diagram E. Then diagram F is there, that is the speed torque characteristics. Rotation angle is available in the x-axis, in y-axis torque is there. So the torque increases gradually and reaches the maximum value, thereby decreases and reaches 0 at 90 degree. So it is rotating from 0 to 90 degree. At 0 degree itself having more amount of torque is there. Almost between 45 degree it reaches the maximum value, thereby decreases and become 0. So the 0 degree itself, that is the the brushes are aligned with main magnetic axis. At that time itself the torque is available, thereby increases. When the alpha increases, it also increases and reaches maximum value, then by decreases. That is almost 0 to 45 degree it is increases, thereby decreases. This refers the diagram E. Now we'll go to the description. It is worth noting that the value of starting torque developed by such motor will depends on the amount of brush shift. So the torque is purely based on the amount of the brush shift. How much brush shifted, that much of torque is developed. Whereas the direction of rotation depends upon the direction of the shift. Direction of rotation and direction of shift are all the same. So that only we refer in the diagram E. Maximum starting torque is developed at the some position where the brush axis make an angle lying with 0 to 45 degree with the magnetic axis of the main pole. At 0 degree itself, some of the torque is available, thereby increases and reaches maximum value, then decreases. So between 0 to 45 we are getting the maximum torque value that we referred in the diagram. Now we'll see the further detail. Motor speed can also be controlled by means of brush shift. So brush shift, so already we discussed, torque is depends upon the amount of brush shift. The direction of motor is direction of the brush shift. So the speed is controlled by brush shift also, right? So shifting of the brushes will control the motor speed. Variation of starting torque of a repulsion motor with the brush shift is shown in diagram F that we discussed in the diagram. So the diagram between the torque and angle alpha. Then a straight repulsion motor has a starting torque about 350% and moderate current about 3 to 4 times of the full load value. So the torque is about 350%. The starting current is 3 to 4 times of full load value. So in this video we discuss the repulsion motor. What is meant by repulsion principle? What is the construction of the repulsion motor? What is the magnetic axis? Vertical, thereby horizontal, thereby inclined with an angle alpha. In 3 cases, how the torque is produced. Then we discuss the torque versus angle, or how the torque is increases. Then, so all the details we discussed in this about the repulsion motor along with the repulsion principle. There is a repulsion between the stator pole and rotor pole. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. All the best for your examination.